Welcome to this technical deep dive into our rock paper scissors game system. In this video, we'll explore the sophisticated architecture behind this seemingly simple game, breaking down the computer vision techniques, user interface design, and game logic that make this interactive experience possible. Whether you're a developer interested in the technical implementation or simply curious about how computer vision games work, this overview will provide valuable insights into modern application design. System Architecture Overview. Our rock paper scissors game is built on a model view controller architecture, providing clear separation between data management, user interface, and control logic. At the heart of the system is the main window class, which serves as the central controller managing page transitions and the overall application lifecycle. This architecture facilitates modular development, making it easier to maintain, test, and extend the game's functionality. The system utilizes a stack-based UI navigation system implemented through QStacked widget, allowing seamless transitions between different game screens. User interface layer. The user interface is designed with simplicity and user experience in mind. It consists of two primary pages, the home page and the game page. The home page provides an introduction to the game and clear options to begin playing, while the game page delivers the main gameplay experience with a real-time camera feed, gesture recognition visualization, and an intuitive scoring system. We've also implemented a custom VS widget component that visually separates and compares the player's gesture against the computer's selection, enhancing the game's competitive feel. All UI components are responsive and adapt to different window sizes, ensuring a consistent experience across various devices. Computer Vision System. What makes this rock paper scissors implementation special is its computer vision system. Rather than using button inputs, the game analyzes the player's hand gestures through their webcam. The gesture recognizer component processes each video frame through a sophisticated pipeline, beginning with background subtraction to isolate the hand. Image pre-processing enhances contrast and applies thresholding techniques to prepare the image for analysis. The system then performs contour analysis, identifying the hand outline and calculating convexity defects to determine how many fingers are extended. A temporal filtering mechanism tracks gesture stability across multiple frames, reducing false positives and ensuring accurate gesture recognition even in challenging lighting conditions. Gesture recognition algorithm. Let's delve deeper into how the gesture recognition works. The system analyzes the shape of the player's hand by detecting contours and identifying convexity defects, essentially the gaps between fingers. For rock, the algorithm looks for a closed fist with minimal convexity defects. Paper is recognized when all fingers are extended, creating a flat hand with maximum area. Scissors are identified by detecting exactly 2 extended fingers with significant convexity defects between them. The algorithm implements a confidence scoring system that requires a consistent gesture over several frames before making a final determination, preventing accidental movements from triggering unwanted gestures during gameplay. Game logic implementation. Once a gesture is recognized, it's passed to the game logic module, which determines the outcome based on classical rock paper scissors rules. Rock crushes scissors, scissors cuts paper, and paper covers rock. The game implements a comprehensive scoring system that tracks wins, losses, and ties across multiple rounds. When the camera detection system encounters difficulties such as poor lighting conditions or when the hand isn't clearly visible, the system gracefully degrades to a fallback random selection method, ensuring the game remains playable in all circumstances. This fault tolerance approach exemplifies our commitment to a smooth user experience regardless of environmental conditions. Camera interface. The camera interface module handles all aspects of video capture and processing. It begins by initializing the camera with optimal resolution and frame rate settings for gesture recognition purposes. The frame capture process runs on a separate thread to maintain UI responsiveness, even during intensive image processing operations. Our robust error handling and recovery mechanisms can detect camera disconnect ions, permission issues, or hardware failures, providing clear feedback to the user and automatically attempting to reconnect when possible. The real-time frame processing pipeline is optimized for performance, balancing accuracy with computational efficiency to ensure smooth gameplay on a wide range of hardware configurations. Data flow architecture. Understanding how data moves through the system is crucial to appreciating its design. When you start a game, the camera captures video frames that are immediately sent to the pre-processing pipeline. These processed frames are analyzed by the gesture recognizer, which determines the player's move. Simultaneously, the computer selects its move either randomly or through strategic algorithms. Both moves are passed to the comparison logic, which determines the winner according to game rules. The results are then updated in the UI, with the scoreboard reflecting the outcome. This entire flow happens in milliseconds, creating a responsive gaming experience that feels natural and intuitive to players. Fault tolerance features. We've designed this system with robust fault tolerance in mind. The camera error detection system continuously monitors the video stream for quality and availability issues. If detection confidence falls below acceptable thresholds, the system provides visual feedback to help the player adjust their hand position or lighting conditions. Should the computer vision system fail entirely, the game gracefully degrades to an alternative input method, ensuring gameplay can continue. All error conditions generate appropriate user feedback, with clear instructions on how to resolve common issues. The stability tracking system uses temporal filtering to reduce false positives, making the game feel responsive yet stable even in challenging environments. Results and history tracking. Every game outcome is stored in a structured history system, allowing players to review their performance over time. The Show Results button triggers a detailed game history display, showing previous moves, outcomes, and statistical patterns. The system calculates overall statistics such as win/loss ratios and most frequently used moves, providing insights that can help players improve their strategy. This data persistence approach enhances replay value and creates a more engaging experience as players try to improve their performance metrics across multiple game sessions. Architecture pattern benefits. Our implementation of the model view controller pattern brings significant benefits to this project. The model components handle game state, history tracking, and score management, keeping all data concerns separate from presentation logic. View components like homepage, game page, and various UI widgets focus exclusively on presenting information clearly to the user. Controller elements manage the game flow, process user input, and coordinate between the model and view layers. This separation of concerns makes the code base more maintainable, testable, and extensible, allowing us to easily add new features or modify existing ones without disrupting other parts of the system. Development methodology. During development, we embraced an iterative approach with frequent testing and refinement cycles. The computer vision algorithms underwent extensive testing across different lighting conditions, hand sizes, and skin tones to ensure reliable gesture recognition for all players. User interface elements were prototyped and evaluated for intuitive interaction before final implementation. Performance optimizations focused on maintaining responsive gameplay even on systems with limited processing power. This methodical development process resulted in a robust, accessible game that demonstrates sophisticated technical concepts while remaining fun and engaging for players of all ages.